All right, so welcome back, and we're gonna finish off this chapter 4, which is about model selection. But as I said, it's really about, in a sense, idealized algorithms that can be derived or designed based on the principles that we learned so far. A particular topic that we're going to talk about today is about convex surrogate laws. So all the things that we discussed so far, either it's empirical risk minimization, structural risk minimization, cross-validation, and forged cross-validation, or regularization-based algorithms, and so on. They all use, they all include the minimization of the empirical loss. Okay. Which is written like this, which was written as if the S is a set, it's a sample of M examples. It's written as like this, Mi is equal to 1 to M. And then number of times we didn't, this hypothesis was wrong, which is written as h of xi is not equal to yi. And then but it turns out, this loss make optimization not very easy. Okay, what I mean by this, a little bit more formal statement is that often when you select a hypothesis class, which is reasonably simple and nice, we encounter the computational problem not because of the hypothesis class, but because of this loss function. The particular loss of this notion of empirical risk that we are minimizing. So I want to make it a bit clear about what's really going on. So I'm going to introduce a symbol L to indicate a loss. So I'm going to write it like this. I is equal to 1 to M. And then this loss of h of xi, yi. So L is really defined as indicator function, which has a value 1. When h of xi is not equal to yi, if they are the same, it has a value 0. Okay? So it turns out, even when the hypothesis set is reasonably simple, this is specific function L causes a problem, computational problem. It makes the computations of minimizing this empirical loss it makes this minimization of this empirical loss NP hard, which means that computation is not very easy. So then that brings us to the following question: can we somehow use an alternative loss, maybe L prime instead of L, then let us avoid this computational history. And in fact, the real-world machine learning algorithms that you encounter, those algorithms minimize L prime instead of L. For the reasons that I'm just explaining to you so far, because of the computational reason. So what we're going to look at this, in this part of the chapter is some criteria that we can use to select L prime, and also some examples of L prime. At the same time, we want to develop some theory which say, how minimizing L prime is related to minimizing L. Okay, so this L prime will satisfy certain property, and because of that property, it's going to be called convex. The property is related to convexity, which makes optimization problem a lot easier. And then because we are minimizing L prime instead of L, this is called the surrogate loss. Okay. But entire discussion of this chapter, make some one big assumptions about the hypothesis set. Okay, so we are not thinking about our hypothesis set H. We are thinking about our hypothesis set H, which is a subset of mapping from input to -1 and +1. But if we are more mathematically oriented, whenever we talk about function, we always talk about measurable functions so that these functions doesn't cause any problem with probability. Okay, so this was the most general setup that we used so far. But in this discussion, and actually in practice, in many of the learning algorithms in practice, hypothesis set has actually more structure. So not the union of multiple models, but each hypothesis in hypothesis set has some structure. So each hypothesis set is often written like, constructed in two ways, two steps. First, we have some class of function f that is a function from x to the real number. You can view this as a function that maps x to some kind of score. And intuitively, if score is positive, that means our hypothesis we're gonna map that specific x to the positive example. If score is negative, then we're gonna map that specific x to the negative example. But this score is much more informative. Instead of just saying plus and minus, it in a sense say, how confident we are about the plus label, how confident we are about the minus label. And as I said, most of the time, hypothesis is constructed in a way that I'm just gonna explain to you. So the hypothesis set is constructed in two steps. First, we have set of function f, then h is defined by these functions. It takes x and then map it to sine of f of x, where f is in this class. Then what this sine function what this really tells us? The sine function maps, if the input is non-negative, it maps it to 1. If input is negative, it maps it to -1. So this whole thing is the same as, so +1 if f of x greater than or equal to 0. -1 if f of x is negative. Okay. So the discussion that I'm going to talk about will assume that our hypothesis set is of this form. So if that's the form, then what can we do? And why we are talking about this? As I said, in practice, this happens all the time. But then, for more theoretical side, if we have something like this, then we can define some L prime, which is the beforehand, L prime is the L that I defined, which measures loss or measures an error for us. One particular example was a mapping from 2y to the real number. Okay. So typically positive real, but it's a 2y to the real number. But if we know that our hypothesis set have this structure, then we can instead use L prime, okay, which is take a real number, some score, and y, and return r. Both L and R prime, they measure how good my hypothesis is with respect to a specific example. So let me just explain a little bit, and these things will become a bit clear. For each of this h in f, we're gonna write h as h sub f to mean that this hypothesis is generated by this function f. So this f is the one that generates this hypothesis. Think of it as I said, score function. So in that case, in order to measure an error, so the one above the error of h of f on sample xi and yi is written as L of hfx, 1. Okay? So that's how we write it. But below, we are now exploiting the fact that h is built from score. So in this case, we can write error as L prime of f of x, 1. And this will be more informative because we view f of x as a confidence about the confidence of a hypothesis about a positive or negative label, then it can provide a much more informative feedback. And also, because it's over the real number, we can exploit some nice structures of the real number and to have a much better behaving L prime. So as I said, in the setup that I'm explaining, we're gonna use this kind of L prime and describe a way to build this type of L prime when our hypothesis has the structure that I explained to you, and then we're gonna analyze it. So now how we can build something like L prime. So here comes here comes the complexity. So how to build L prime. By the way, if you have L prime, then designing an algorithm in some sense is, follow the same principle that we discussed so far. L prime measures, the error in some sense, and then all the algorithm will designed to minimize these errors measured by L prime or some modified version of L prime that incorporate some information, the complexity measures on the hypothesis and so on. Okay, so if we have a L prime, algorithm is designed to minimize L prime. So now the question is how to build L prime such a way that this, what we are doing also still related to the original L that we discussed so far, original empirical risk minimization. At the same time, it is a computationally easy. So here's a recipe. The recipe is using function v that goes from the real number to the real number. But it satisfies a few properties. The first property it satisfies is that it's complex, which means if we have a phi minus alpha uv, so alpha is the, this is boundable by for alpha, which is a number between 0 and 1, and then u and v are the real number. So in some sense, what this one really tells us is that this function phi is of the, which looks like this. Okay. So if you have take a 2 number, which is 2 input value, which is u and v, and then if we take some points w in the middle based on some ratio with alpha and 1 minus alpha, then computing these two values and computing its average, which will be here, will be always higher than computing the value of this function at the same point. I think my pictorial explanation is a bit confusing, so I mean, don't worry about this. So another way to understand this convexity is it's almost like a linear function, except that in the linear function we have equality, in the convex function we have none, this is less than or equal. And good thing about convex function is that it always have minimum value. I mean, it's very easy to find the minimum if our function is convex. Now the second property is that okay, when the function has a minimum. Okay, the second property is that this function phi is non-decreasing. It means the following: if the u is less than v, that implies phi of u less than equal phi of v. So it's never the case that for larger inputs, phi becomes smaller. So that's the second property. The third one is quite important. The third one said for if we have a take an indicator function, it's bounded above by phi of minus c. So it's what is stated, what this one describes is if I draw this function, the function looks like this. If for the inputs, if the input is non-positive, it has a value 1, including the case when u is equal to 0. But if as soon as you become positive, its value will become 0. Goes like this. And then the other side, I mean, this inequality say my function phi should be if you flip the inputs, it should be the upper bound. So function should look like this. It's a convex function, so then it's non-increasing. So that if you put a minus sign, all the things will be flipped. So it's an upper bound of this function. And then, so essentially all these conditions say the function phi with minus sign will look like this. So how does this help? So then given this, we're gonna define L prime, which take the real number and appropriate label, and then some measure which say how well we are doing. It follows. Say L prime of the real number R, and then label Y, be written as B of minus R number. And then we'll say this will be the measure of an error that we're going to use. Okay. Then, I mean, the first question becomes, okay, why does this make sense at all? Okay. So, I mean, to see why this makes sense, there's just some results that we can first show. And the result goes like this. So if you go with the L prime, we can now define the empirical loss of a function. So if we have a, let's instead of writing L prime, let's write it like this. L sub v. Sometimes I use p as a subscript, sometimes a superscript. I mean, it's a bit confusing. But we're gonna write some new type of empirical loss of our hypothesis h of f using L sub p. How we do it? I mean, S, as usual, is a sequence of input-output pairs. And define 1 over m and then the error measured by the error measure that we just defined. LV of alpha and f of xi and 1. As I explained to you, we are exploiting the fact that our hypothesis is constructed from score, so we just directly access the score and then compute the error measure in this way. And if we do so, then compare this with the usual notion of error that we already know, so which is an empirical risk of h of f. It's written as 1 over m. So go to 1 to m. I use the notation that I showed you before, xi, yi, where L, this is the same as hf of xi not equal to I. So then there are the few questions. The first question is there should be some relationship between what we just defined, which is this quantity, and then what we used before, which is this quantity. Yeah. What's going to be the relationship between the two? That's our first question. And the next question is, why we are doing this? Is if we use this new measure, is there something going to be easy and so on? So let's just start to look at the relationship between these two error measures first. So here's here's a relationship. One lemma, say R S of h of f is always upper bounded by v s h of f. So sometimes people use the word surrogate to means, not always, but sometimes people use the word surrogate to means that the new things that they came up with actually provide an upper bound of the old things that they have to really deal with. Okay. So that's the case here. So, now proof. I think the best way to, this is not entirely, kind of one-line proof, but it requires some calculation, but it's not very difficult. So I will give you 3 minutes to prove this lemma. So the key of the proving it is actually using this third property. So try to prove this lemma. Okay, so let me show you the proof. Actually, the proof is it's quite easy. So we just do the calculations. Our head S of h of f is defined by 1 over m is equal to 1 through m. Using L, but we expand the definition of L. That's written like this. And also expand the definition of h sub f, which is a sine f of xi is not equal to yi. But then it turns out this one is bounded above by the following function. So m, we multiply f of xi and yi. If it's non-positive. If it's not positive, then this indicator function return 1, otherwise return 0. Okay. So why we have this upper bound? The reason we have this upper bound is that if this f of xi is not 0, then this indicator that we define on the left-hand side, the indicator that we already have, and then the indicator that we newly define, they become exactly the same. I mean, if fxi is either positive or negative, not 0, so then its multiplication with yi will become negative, because yi is either +1 or -1. It's gonna be negative when f of xi and yi have different signs. Okay, literally, excluding 0. So that's exactly correspond to the one on this side. Now, when f of xi is equal to 0, this right-hand side will always have a value 1, and the left-hand side is have a value either 0 or 1, so it's going to be an upper bound. So modulo the 0 case, the right-hand side is a pretty good approximations of what's happening on the left-hand side. Now, because then after this, we can use the equality that I mentioned to you above. And if we use that inequality, then we can get next step, which is 1 over m summation I is equal to 1 through m v of minus f of xi and yi. And that is, really according to our definition of the new loss is Lp of f of xi and yi, which is exactly our new empirical loss with respect to p. So that complete the proof. So what this theorem tells us is that the new loss is an upper bound. Okay, so optimizing the new loss in that sense makes some sense, because ultimately we want to minimize we actually want to minimize the real loss, but empirical loss is often good kind of alternative that we can minimize. But here, this lemma tells us if we satisfy the 3 conditions that we described so far, and we define loss using phi, and optimizing phi is a sensible alternative. Actually, you can confirm, provide further justification about why doing this is okay. So let's move to the next. So then the next justification we can think about is the following. Ultimately, what we are really interested in is generalization error, not empirical error, generalization error. And then we might say, how is it going to be related to generalization error? That's constructed using phi. is there any relationship between the two? It turns out there's a relationship between the two. So now I have to define what tell you what this guy is. It's defined in a very similar way to this R of H of F is defined. This is defined as average error, average loss. So H of F, Xi, X. Y. Here X and Y are sampled from a known distribution. This is the same. It's an expectation of X and Y are sampled from unknown distribution. Now we are measuring error with our new loss using the score part of a hypothesis. Then this relationship is true, and then it follows by the same reason that I explained before. No, there's a different color. So okay, it's not a lemma. The proof is essentially the same thing, but so just for practice, let's just write the proof. So it's R sub F defined by expectation. So if we unpack the definition of L, that's saying this one, sine of X is not equal to Y. Then we use the same inequality. Essentially, the proof is the same. F of X, Y is not positive. Indicate the function which have a value 1 when f of X times Y is not positive. Then that's bounded by the third property of function phi of minus xy, and that is exactly this part is exactly same as loss y, so that is the same of h of y. So it's not superscript. So essentially the proof is the same. So this gives another justification of why we are doing this makes sense. I mean, using the new error or new empirical error or the new generalization error based on phi, they all provide an upper bounds of the old stuff that we have been discussing so far. So I'm going to give you a bit more thorough justification, which also guide the choice of a sensible phi. So far, to use this theory, you have to pick phi, which satisfies the three conditions: non-monotonicity, non-increasing, non-decreasing, and then convex, and then the third condition that I told you. But then there will be one more condition which provides a bit stronger guarantee. And it turns out that people design or use in practice, many things that people use in practice satisfy all these conditions. So these two lemmas say optimizing our new empirical loss makes some sense. Okay. So then the next question we have to address is optimizing this new empirical loss is going to be easy? And the next lemma, provides some indication that is it really the case. What this lemma says is the following. It says that R P sub S, because this is the quantity that we are optimizing. So let me just check. So it's a quantity that optimizing is convex. By convex, I mean the following. Which this means if we have so we have construct H, but by combining two square functions using alpha, and if we do so, that is upper bound by this. So here, f and g are in our function class f, and then alpha is some number between 0 and 1. So this is what I mean by convex. And so this lemma indicates, it doesn't really tell you at this point why optimizing using this new loss is easier, but it does give a good indication why optimizing new loss with this new empirical loss functions is going to be easy. In particular, if f and g are linear function with and then our hypothesis set is set of linear function. So each hypothesis is parameterized by the coefficients of the linear function. Then this convexity means that our loss has is convex with respect to parameters of our hypothesis. So if you don't understand what I'm talking about, it doesn't matter at all. This is a property that can be exploited to design a more efficient algorithm. So it will let us avoid this NP hardness that comes from the original loss function. Then the proof is again quite easy. So we can use convexity assumption of V. So just try this. We have a R V S H F 1 minus alpha G. So then that is same as 1 M is equal to 1 through M. And then it's the new loss, but if we expand the definition of new loss, it's going to be just V applied to minus yi and h of alpha f xi plus 1 minus alpha g xi. But if we can rearrange this whole part, the input to phi as follows, say alpha times minus yi f of xi plus 1 minus alpha times minus yi g of xi. So then now we can use convexity of the function phi. Then that convexity allows us to, in a sense, move this alpha and plus outside, but then things will become larger. So if we do so, then we have 1 over m summation I is equal to 1 to m alpha of e plus 1 minus alpha e minus yi g of xi. And that's exact. So then if you, just move this summation sign, that's exactly the alpha of r p of s h of f plus 1 minus alpha r s p h of g. So it satisfies the convexity property. Okay. So provided, the third condition allowed us to have an upper bound. The first convexity condition allows us to have a convexity. So they deal with these computational issues, and then the computational issue, as well as it allows us to connect what's really going on here with what happens with the empirical loss and generalization, empirical error and generalization error. All right. So then before going further, let me show you some examples. So what are going to be, so we didn't use this second non-decreasing property, and that non-decreasing property matters when you do more, difficult analysis, which I'm gonna tell you soon, okay? But before doing so, let me just show you some example of the field. So, 6. What are going to be the examples? So one example is called the hinge loss. And in this case, the function phi is defined like this. Max 0 and 1 plus. So if we draw functions phi of minus u, because that's what we are using all the time, the function looks like this. If it's the value of u is greater than 1, it's 0. It's 0 here. But if it's from value of u is equal to 1, it starts to grow and then it becomes a line. It's 1 here. So you can see this provides an upper bound. It satisfies the third condition. Also, if you have a geometric intuition about convexity, it's a convex function. And the second condition about the non-decreasing, if you flip the sign of the input, that corresponds to non-increasing property, and it also satisfies the non-increasing property. And then the hinge loss is used of, in the design of the machine learning algorithm. Then the second is an exponential loss. So in this case, the function that we are using, so the function that we are using is just exponentiation of u. So again, if you draw these functions, the p of e and minus u, it will look like this. The touch. So I think my drawing is not very good, but it's on the exponential function. So what you compare to the hinge loss, one thing you can immediately see is that if the score is, the score is the going to the very negative side means something is not quite right. Score, it has to be produced positive values, but it produces the large negative value. So something is not quite correct. In that case, hinge loss give a linear penalty, exponential loss give an exponential penalty. So it will encourage to make an improvement for this large error case a lot more. Okay. And then the third one is logistic loss. So it becomes very much like so-called soft cloth function using the neural net. So in this case, u is log 2, 1 plus e of u. So this function becomes a bit like a hinge loss, except that it's smooth, it's differentiable, and it has a nice smoothness property compared to the hinge loss, which is not differentiable when the input is equal to 1. Hinge loss is a lot smoother. And then its behavior is quite a bit similar to the hinge loss. Okay. So it doesn't penalize the large errors as much as the exponential loss. Okay. Right. So then these are the possibility. And then can you say a little bit more about these options, and then do somewhat kind of the real analysis about what's really going on when we use these surrogate and convex surrogate losses. Talk about this. Let me just move to the next part. Just use 7. So now we can do some theoretical analysis. So what we want to analyze here. So one thing we want to analyze is that, if you remember what we did before, our theoretical analysis was based on so-called excess error. So if we have a hypothesis, then we consider the error between our hypothesis and the Bayes risk, which is something that means the best error that we can achieve. Even when we ignore the hypothesis, so this is the best error we can achieve. And then we do something, try to analyze this quantity in terms of estimation and approximation errors. And then we design various algorithms that give an indication about what's really happening on this excess error. But it turns out we can do something very, very similar with our new loss. So in this case, they are all based on the loss L that I talk about, which compares with whether the label is correct or not. But we can do something very similar for the, our new loss L sub v for the convex non-decreasing and then some kind of upper bounding function v. In that case, we can use this quantity that I explained to you, which is expectation of minus y f of x, and that is our loss f of x. Right? And then it turns out we can also define something that we can achieve the best. So this is, say, we ignore hypothesis set. We consider all the measurable functions, measurable score functions. So instead of using f, we are really using all the functions from x to real number. And then we can try to find something that achieves the minimize this new field-based risk. Okay. So that's a minimum that we can achieve. Then we can think about this new version of excess error. So let's call this as a phi excess error. And then we can design an algorithms or design some strategy that attempt to minimize this phi excess error, maybe design better hypothesis set and so on. But then the question becomes, how is it going to be related to the original excess error that we talked about? It turns out if this function phi satisfies some property, then these two things are closely related. So here's theorem that I'm gonna explain the theorem. 4.7. Sorry, I think the convention is to use. Okay, so it's a theorem 4.7. So it has some condition on phi. But if the condition is true, its conclusion is quite interesting. The conclusion say the following. It says that for function f goes from x to r, the all square function, then satisfy the following property. If we measure its excess error, it's going to be bounded and has a power of s to c s, and excess error with respect to b. So then the values, the condition values like s and c will be determined based on the function phi. So also there are some conditions about phi here. But what it tells you is quite interesting. It say that the excess error, which is some ultimate errors that we perhaps care about, with respect to the original risk, I mean the original kind of success criteria that we have, actually is closely related to the excess error that we can, we can look at by using much more computationally friendly versions of the error based on this our function phi with convex non non-decreasing and then some upper bounding function. Okay. When this function phi satisfies some property, and furthermore, this property turned out to be satisfied by all the function, all these losses that I told you: hinge loss, exponential loss, and even some version of the square loss and so on. They all satisfy this condition. Okay. So they all have this very nice property. So then let me explain a little bit about these theorems and then maybe finish the discussion of this chapter. So then so there's some component of the theorem is this guy. I said there is something best we can achieve. So this is how can we do this? Okay, so what's going to be the best functions that minimize our new notion of risk? It turns out we can define this. If we have a function f, so it's a function that takes input x and return the real number. And we can define function f like this, given x. So here we are assuming there are some fixed distribution d. Okay. So the problem is fixed. Otherwise, we cannot really talk about the best, best this scoring function or the best error that we can achieve or minimum error that we can achieve and so on. So d is fixed. Okay. So if we have a f function f, what it has to return is a minimum. So actually, it's not return real. It's a return extended real. It can be minus infinity and plus infinity. So there are some mismatch, but I think all the things that I described can be extended by including this minus infinity and plus infinity. So then this f of x is defined by the minimum. So argmin u minus infinity and plus infinity. So we'll return u that minimize what I'm going to describe to you. And it's minimizing this quantity, eta of x phi of eta of x phi of minus u plus 1 minus eta of x. here eta x is the probability that y will have a value 1 given x. So because this d is a fixed and this d is a distributions, probability distribution of x and y, we can think about conditional probability of y given x. So so eta of x is computing conditional probability when x is fixed and the value of y is equal to 1. So 1 minus eta of x will be the conditional probability when y has a value minus 1 given x. So if we compute this, so this means that we have to pick u that minimize so the quantity that I described here. Okay, so that's what I'm gonna write it as like f star. And it turns out if you do so, then this r p of f star smaller than or equal to r p of f for every functions from to the real number. So I said the more strict is a measurable function from x to the real number. Okay. So then why that's the case? I mean, if you think about how this f star of x behave, we say that if eta of x is large, which means that the conditional probability, the given x, y is more likely to be 1. So then we will pick u such that this phi of the minus u will become small. And I mean, in return, we may have to make phi of u will become large. But phi of minus u becomes small. I mean, this is the penalty that we pay when we didn't get, when we make a mistake when y is equal to 1, this is the penalty that we are paying there. So this means that we try to find the u that has the smallest penalty when y is equal to 1. And otherwise, so if eta of x is really small, so that the probability that the chance y has a minus 1 is large, then so y is large. So I think my explanation got messed up. But anyhow, if this minimization really say if y is likely to be 1, then we should return u, which have in line with this y has a value 1. If y has a value 0, y has a value minus 1, then we should return u so that the penalty, we pay the minimum penalty in that case. So don't worry about my explanation. I mean, you can just take this as a definition, and then one can show this is a minimum. And about 3 minutes. So I mean, one can easily show this is a minimum. You can just use the definition and then just doing some simple calculation that will allow you to prove this is the minimum. Yeah, I have to think a little bit because there's more things that I prepared. So given this much, now we can show the following. So I think I wrote it like sub P. So then here's a theorem. And then here's also a reminder of what happens in the typical case. Okay, so we can also define f star Let's do this case, just a real number. Such that the risk of star is same as risk of H of F star. It's the same as Bayes risk. So this is we can, so the one above is the score function that we can choose, which minimize our new errors, the new error defined by phi. Therefore, we can also define phi star that minimize the old error that may produce the hypothesis which have the Bayes error, which means the minimum error that we can achieve. And how it's defined, its definition is quite easy. So eta of x minus 1/2. So if we do so, then do the calculation, we can show that this is as good as we can get. So we have two functions. One for f, maybe just write as the real statement that we care about. This is so it's a minimum that we can achieve with respect to phi. And the one that I define is produce the minimum error that we can achieve in the standard sense that we discussed until discussed so far. So then the theorem 4.7 say the following. So one accurate statement of the theorem. So the theorem say the following. It says that if there exists some s is greater than 1 and c is greater than 0, such that some property is true for every input f star of x is bounded above by c of s and b0 minus expectation of y given x also star of x comma y. So if this relationship is true, then for f we have the following. F h of f minus r star is bounded above by. So that's the theorem. And as I said, the conclusion is quite interesting. It's the excess error in the old sense. So there is it's a excess error in the old sense is upper bounded by the excess error with respect to phi. Modular, there are some exponentiation and some extra constant that's being put here. Okay. And the exponent is the power s and then extra constant c really coming from the relationship on the actually only for the optimal value. So we said we are comparing two optimals, one for in the two optimal square functions of f of f star, and then this f star sub p. If they satisfy this relationship, then this conclusion is true. I original plan was to go through the proof, but looks like I don't have much time. But then I think a bit better way to appreciate this theorem is actually try to prove these assumptions. Okay, this, as I said, this assumption does hold for all the three examples that I showed you. So here are, in the remaining 4 minutes, I want you to solve the following exercise. First exercise is this. Exercise. The first exercise is to show the assumption of this theorem 4.7 holds for, actually not first, but for these two functions, two convex functions. The first one is hinge loss. So U is max 0, 1 plus U. The other one is actually coming from the exercise, the second exercise, which is U is 1 plus U squared. This is a bit like a square loss. Okay. For both of them, this condition holds. The second case, S is equal to so S is equal to 2, C is equal to 1 over 2. So in the first case, S is equal to 1, C is equal to 1. So show that in this phi with this extra condition satisfy the assumptions of theorem 4.7, phi with the different phi coming from the square loss with this extra S and C also satisfy the assumption of theorem 4.7. So remaining 2 minutes to solve this, and then I will give you, I don't think I can have a time to go through the entire answer, but I will give you some idea about how to solve this. Okay, so here's some hints about how to solve these two problems. For the second problem, you can actually compute what f star of v is. Because, I mean, this v is a quadratic form, and then this eta of x, once x is given, they are constant. So, I mean, you can find the minimum of this entire quantity by just using the minimum value of the quadratic form. So you can get rid of min in its definition, and then argmin its definition, and then get some answer. And if you plug in that answer, then you can show that this condition can be discharged. For the number one, you just need to do case analysis. So again, I mean, all these questions boils down to how to deal with minimum. So, I mean, this argument, how to deal with minimum. But if you do the case analysis on U, then you can find a better descriptions about, again, what this f star of v of x actually looks like. Then if you plug in the definition, then you can again prove this theorem. But the one interesting bit about this theory is that usually the theory that you can encounter in the machine learning, they are quite far from the practice. I mean, they impose a lot of conditions. But these loss functions like hinge loss and so on, they are at least some of their variants you will encounter when you do the day-to-day kind of work on the machine learning. But what's interesting is that we can actually prove some interesting non-trivial properties about this. Okay, so that's it for today. And next, I mean, we are not going to have any midterm, so next week we can take a week off, and then we will meet. I'm going to meet you again on a week later. Okay, so thank you very much. So see you later.